Um, Good afternoon, everyone. It's my pleasure to welcome on behalf of IGC Conference 2021 in this very big session, this whole conference, because we are having big stalwarts in geotechnical field. I hope this session will be fruitful for everyone, and most of the people will expect for this session. I'm very happy to be session coordinator for this session, and I wish to welcome Chair Professor S. Gandhi, Co-Chair Anirudhan sir, and brilliant speakers Elambari sir and Professor Susan, and IGC Chairman Professor K. Muthukumaran, and our native faculty members Aiduraman sir, and most importantly, delegates of this conference. I welcome once again for this wonderful session. Before starting this one, I'll just give a brief biodata of chair and co-chair. First of all, our chair, Professor S.R. Gandhi sir, is former director, SVNT Surat, and currently working as a visiting professor in IIT Gandhinagar. And sir's major research area is design of pile foundation, ground improvement, field instrumentation and monitoring, and design of ASPAN. And sir served as a member of BS CP 43 on foundations and IRC 78 on bridge foundation. Also, sir served as a chief editor of Indian Geotechnical Journal during 2005 to 2010, and also served as associate editor of Southern Journal. Sir, we are welcome you for this wonderful session. And next co-chair, I welcome Engineer IV Anirudhan, is the director, chair of the DFI Indian Regional Chapter. So, Mr. Anirudhan manages geotechnical solutions in Chennai, a general investigation and consultancy firm. They have conducted many small and medium geotechnical investigations works in Tamil Nadu as well as part of South India. And is closely associated with the IGS activities and was the secretary and chairman of the Chennai chapter of IGS. Also, he had the masters in IIT Kanpur, master degree in IIT Kanpur. Was worked as a quality control engineers as well as served many industrial projects in terms of several deep foundation techniques during his long professional career. Welcome you, sir, for this book.
Thank you.
Now I'll hand over the session to chair and co-chair to introduce about many speakers, and session to you, sir. Professor Gandhi, sir, please.
So, good afternoon to everybody. It's a pleasure for me to join in this fourth plenary session today, where we have two eminent speakers. It's unfortunate that last 2 years we have not been able to meet physically in this event, and we have to have this virtual conference. I'm sure the situation will be better next year and we will be able to meet in person. I welcome all the delegates and all the members of IGS who are attending this online or in physical mode. This session being of 70 minutes, we propose that we give each speaker about 25 minutes time for presentation, and we'll have very limited 1 or 2 questions from the audience if the time permits. And then after both the talks are over, I will request co-chair to give his remarks, and then he will wind up. I mean, then we will be able to wind up session within the allotted 70 minutes time. So I think today, as you are aware, we have very important 2 lectures. The first one, we will start with Professor K. Ilamparuthi's talk, and he is talking on response of passive pile and pile groups with axial and tie forces. It's a pleasure to give a brief introduction of Professor K. Ilamparuthi, though he doesn't need introduction among the IGS members. Professor Ilamparuthi is faculty in the Department of Civil Engineering at College of Engineering, Guindy, Anna University, for more than 3 decades. And he has been known for his research and consultancy activities. He obtained his PhD from IIT Madras almost at same time when I was also a PhD student at IIT Madras, and we still recall working together for various experimental works, and he was very hardworking under Professor K. Muthukrishnaiah. He got PhD under capacity of anchors. He obtained his PhD, and after PhD, he has been working with Anna University. He has received several awards for his research and his works, including the Commonwealth Fellowship. He worked as University of Liverpool for 13 months, and he visited several countries. He is an active consultant involved in the important projects within the state and outside. He has published more than 200 research papers, and he has held various posts, including Dean in charge, Director, Chairman, Dean of the Department of Civil Engineering, Head of the Division, and so on. He has significantly contributed to the IGS Chennai chapter in particular, and to the IGS parent body in several ways. And he, because of his activities at IGS Chennai chapter, the Chennai chapter has got several awards to its credit. So I'm very pleased to welcome Dr. Professor Ilamparuthi for this talk, and I request you to now take over. Professor Ilamparuthi, please.
Thank you, sir, for your nice words. Sir, am I audible?
Yes, sir.
My slide is visible to all?
Yes, you can make it to show mode.
Yeah, it is in this mode only, no, Professor?
No, you have selected the other screen. You have to select the. You select the edit mode. Then after coming here, you can show it as show mode.
In your screen, you see full screen, Professor Ilamparuthi?
Yeah, I'm able to see full.
Because of speed, it takes some time to get full screen here. Maybe you withdraw your screen and reshare it after making it full screen.
1 minute. Hello? Is it all right now?
No, not yet.
I suggest that you come out of the PPT.
Yeah, I came out. Okay, now I'm sharing.
You share the edit mode first.
Okay.
Then you make it full.
1 minute. On a pen. Share edit mode.
PowerPoint. Share. Okay, now all you have to do is click on. Now it's there, and you can essentially navigate this way. Or you can navigate by clicking.
Wait. Is it all right now?
No, it's still in edit mode.
So, sorry, could you repeat that? What is it? What mode is it in?
Edit mode.
No, just we are not able to see the slideshow mode. Please make it in slideshow mode.
It is in the slideshow mode. You're not able to see it right now?
No.
Okay, just give me a second.
So
can you please check the screen, sir? Which screen you want?
Otherwise, you can do one thing. You can share your whole window. Then you can open the PPT in the full screen mode. In the share option,
Can you see the presentation now?
Yes. Now you use the same. Yeah. From there you start the show mode.
Now can you see full screen?
No, it's not
No.
coming. What I suggest is you go ahead with your lecture.
Yeah, let it go, sir.
We can enlarge the screen to see your slide full on our
Okay.
screen. Okay.
Okay, this might help a lot. Can you see the full screen?
Yeah, now
Yeah,
it's
now-
fine. Yeah.
And now it's fine. Okay.
Okay, now please continue.
Okay. Good afternoon to chairman, co-chairman, president, and the EC members of Indian Geological Society, the organizers of IGC 2021, fellow delegates, and dear friends. It is indeed great pleasure in delivering lecture in the midst of geotechnical experts. I feel privileged and honored for the invitation extended by the organizers of the conference. And my topic of today's presentation is response of passive pile and pile grooves with axial and tie forces. I feel this topic is appropriate in the present context of underground constructions, particularly in Chennai. What am I going to talk on this particular topic? It is the content of the topic is given below. Scenario of metro construction. Motivation for choosing this topic for the research. Conceptual response or supported deep excavation. Response of structures in the nearby locations or deep foundations. Scaling law and model studies. Parameters considered for the study. Results and discussion. Numerical simulation and analysis. Finally, conclusion. If you look at the scenario of metro construction all over the world, on November 2021, total metro systems are 198 in 28 countries. Total length is 17,170 kilometers. The oldest metro was London Underground Metro, which was constructed in the year 1863. Total length as on date is 405 kilometers and the number of stations 272. Countries more than 10 metros are China 43, USA 15, India 13, Japan 13. As on date, under various stages of construction, in China there are 7 metros and India 8 metros. All these metros are expected to complete within the year 2025. The share of the total metro length as far as the country is concerned, the China alone shares 39%, the India shares only 4.5%. Therefore, definitely India has a very good scope to go for the metro constructions in order to provide good facility for the common public as well as to encourage multimode transport. If we talk about the scenario in India, the first metro in India was at Calcutta. It was dedicated to the public in the year 1984. The length of this metro is 38.5 kilometers, the number of stations 33. Longest metro in India is Delhi Metro. Again, it was dedicated in 2002. The length was 348.7 kilometers. Total stations 230, now it is 254. The shortest metro is Ahmedabad Metro. It was dedicated to the public by our Honorable Prime Minister Modi ji in the year 2019. The total length of the metro is 6.5 kilometers and number of stations is 6. Now in Chennai Metro, year 2015, length is 54 kilometers and station 42. What is the motivation for choosing this topic? The problem is multifaceted. The geotechnical engineer has a lot of challenge. And then the metros are constructed, the places were called economical hub of each state. The figure on the left-hand side shows the scenario of Chennai city. Selection of alignment itself is a challenge. Apart from that, the geotechnical engineer has a problem to ensure that the safety of neighboring structures all along the alignment as well as at the locations of the stations. On the right side figure shows the failure in Bangalore when the depth of cut is about 4.5 to 5 meters with a slope to cut. The building is totally collapsed. Similarly, if you look at the figure, it is a collapse scenario of a building of ground plus 30 story in Shanghai. The building is supported on spun piles. For the purpose of garage, the excavation was made on one side. Naturally, the face of the excavation was not, because the face of the excavation was not protected, there is a movement of the soil. Adding to this, something like adding the problem, the excavator soil was stored on the other side of the building. Naturally, it exerts the pressure and causes the deformation. Adding fuel to the fire, again, the piles are subjected to movement. On one particular day, there was a heavy rain. Because of that, there is a loss of strength. The whole structure came down, as shown in the figure. Similarly, the Wong has reported the failure of a slope. It's a pile groups completely instrumented, and then they wanted to understand the response of the pile group when there's going to be a unstable cut that was demonstrated in this figure. And then in Chennai, during the time of construction of the metro, on weekly basis, there was a lot of news in the paper about the problem. Metro rail tunnel has damaged 300 plus buildings since mid-2012. Similarly, there was another report that Tamil Wesley Church, it is 152-year-old church, has given away. And then I had the chance to advise the owners of the church. And then again, cracks are reported in building all along the metro rail route at Mannadi, High Court, Nehru Park, and many places. On the left side, you can see a building, the distressed building, which is in the central part of Chennai, that is at the station Chennai Nagar. This is another building. Actually, it is a education institute at one of the important station at North Chennai. The crack in the walls of the first floor, crack in the roof. I had an opportunity to offer my support through the subcontractor. This is the building. It is a ground plus first story building. In order to drive the sheet pile wall for the protecting the building, initially they were not able to drive the pile because of the soil is hard on the top layer. They drill a hole to a depth of about 5 to 6 meters for the purpose of driving the sheet pile wall. The initial crack was formed on the floor, and then soil exhibited the failure as shown here. It is a probable movement of soil mass due to augering as a first stage. Without having proper knowledge, they have grouted the soil to a depth of 6 meters without giving any prop or the strut to the sheet pile wall. Sheet pile was driven and excavation was commenced. Again, you see that the probable slipline of soil was due to excavation without strut support during the second stage. These are all the reasons that has motivated us to study the performance of the passive piles. The conceptualization of the response of supported cut and then the neighboring building has been given in the figure as per TANG 2014. You see that the building adjacent to that of the supported cut. Now the figure shows the vectors of the soil movement. Then there is going to be a lateral movement profile induced beneath the building foundation, as well as the vertical movement induced beneath the foundation. This is going to be the settlement trough. This settlement trough has been already idealized by Pegg in case of cantilever sheet pile wall. The maximum deflection is going to be at a distance of 0.5 times the depth of excavation. And then the primary influence zone will be to a distance of about 1 times the depth of 1 to 1.5 times the depth of excavation. And then the secondary influence zone will extend to a distance of about 4 times the depth of excavation. This is the profile in case of strut supported or braced cut supported, where you are having the sagging mode. Whereas if it is going to be a cantilever, it is going to be in a hugging mode. Now, I wanted to highlight what is the difference between the active and passive pile system. When you apply a lateral load, you see that this is the soil movement and pile movement. Otherwise, I can say that the interactive response of soil and pile, this is the way the passive resistance will mobilize. So, the lateral force is acted on the pile and the pile is undergoing a deformation that we call the active pile. Whereas the soil movement exerts the pressure on the pile or load on the pile, then we call it as a passive loading on the pile. This is the figure which shows the ground displacement on one side, but really the problem of deep excavation is going to be, we are going to excavate here. Therefore, there is going to be a stress reversal. Whatever which is going to be, whatever is shown here, it is going to be totally reversed. Now you see that the modes of failure of the support cuts. It's a cantilever mode when the sheet pile wall or a diaphragm wall is not having any support. It's a kick-in mode where there's going to be a yielding of soil at the toe level of the sheet pile wall or pile. Then this is the properly propped diaphragm wall or a sheet pile wall convex mode. Again, this is a composite mode. If there's going to be any yield in the top strand, naturally there is going to be some amount of movement. It is going to be a combination of both cantilever as well as the convex mode. That's what we call it as a composite mode. But the present discussion only based on the cantilever mode problem. In order to go further on this, the selection of parameters are very important in order to do the model study. 1G model study test was conducted in this investigation. The parameters are depth of excavation DE, depth of support system from the ground level LR. These two parameters are very important. In order to decide these two parameters, the classical analysis was done for various depth of excavation by considering different density of the soil mass. And finally, we found that the DE by LR ratio is 0.5. For the factor of safety of 1.5 to 1.2 is needed in case of loose to dense sand, which is very well supported by Winterkorn and fan. Whereas in case of dense sand, which is needed in terms of about 0.6 times. That's what the other parameters are diameter of the pile, length of the pile, location of pile, that is distance between the pile and then the supporting system, configuration of the pile group, both square and rectangle, and number of piles, nature of deposit. In this study, we have considered the medium dense sand. We all know there is a scaling problem in case of 1G model. The stiffness of the soil pile system depends upon the stress. The stiffness is equal to sigma times alpha. The Wood suggested a model. He has given the stiffness response EM by EP is equal to 1 by n power n plus alpha, where the n power alpha, whatever we have, sorry, this is going to be 1 by n power 4 plus alpha from the experimental findings of 1G model as well as the prototype. With the experimental evidences, he is recommended that alpha value can be used as 0.5 for sandy soils, and for clayey soils, alpha value can be used as 1. Hence, the scaling factor for various dimensions has been presented here. Based on that, we modeled a pile of 550 mm diameter RC with various lengths. In order to satisfy the scaling law, what we adopted based on the Wood's recommendation, the results of Liang et al. On a centrifuge model, which is accelerated at 50 G, has been taken. It is scaled down, and then analysis was done. The result was compared. The figure shows the prototype response of Arthurs and then prototype response of Liang that supports the Wood's model will work better to extrapolate the results of 1G model test to the prototype. This is the facility developed to carry out the 1G model test in the laboratory. This is the test tank of size 100 mm by 60 mm. Sorry, 100 centimeters by 60 centimeters. We have the sheet pile wall, and then system for applying the axial load to the pile group, and the system to apply a tie force. The axial force and tie forces are varied in order to understand the response of the passive piles. The test was conducted in a medium dense sand with a relative density of 59%. The unit weight of soil, its average unit of soil is 16.5 kN per meter cube. The angular shear resistance of 35 degrees. Now, I will be presenting the single pile and pile group response one after the other. This is the schematic arrangement of the excavation system simulated. It is not like a large shear box test where the hinge arrangements made at some level of the box and then the box is pushed on one side. Instead of that, we try to simulate the actual excavation condition by means of a supporting system. By removing the support one after the other, then we can, stage construction can be done. That's what. The important parameters are the maximum displacement of the pile, maximum bending moment in the pile, spacing ratio between the pile and then the support system, excavation depth ratio, pile embedment ratio, pile flexibility factor, soil yield pressure. These parameters are used for non-dimensionalizing the what are the observations made. Next. This is the response of the single pile. This is the normalized displacement with the L/D ratio. For the short pile, otherwise the rigid pile having L/D 10, the displacement is higher. the displacement drastically reduces with increase in LBD ratio. When the LBD ratio is more than 20, the non-dimensional parameter is almost asymptotic to that of the LBD axis. It indicates the flexible pile response is better than that of the rigid pile. The parameter delta has been non-dimensionalized as done by the Brahms using EA of the pile as well as the coefficient of modulus of variation. Now the deflection response, non-deflection response has been presented here, or L over D. Otherwise, I can say that it is a pile embedment ratio as well as the ratio between length of the pile as well as and the length of the support. As the length of the pile is going to be more and more than that of the length of the support, the pile is stable. Similarly, the length of the pile is more than that of the depth of excavation. Again, the pile is more stable. This is the bending moment variation of the short pile as well as the longer pile. The bending moment is maximum, very close to that of the bottom of the excavation, irrespective of the spacing of the pile. The closer the space, the location of the pile is closer to the sheet pile wall, and the moment is higher than that of the pile away from the sheet pile wall, irrespective of the LBD ratio of the pile. The moment of the pile has been normalized using the passive resistance of the pile. Now we can see the normalized moment with reference to the normalized depth of excavation. The moment, the normalized moment in the rigid pile is more than that of the flexible piles. Now, the normalized moment has been represented in another way, that is the ratio between the spacing of the pile to that of the length of the pile. From this, we can see that the moment is reduced with the increase in the spacing distance. However, if you look at the figure carefully, the moment is the same for a given ratio of SRP versus DE. Now, we are presenting the response of the 4-pile group. Again, this figure compares the displacement response of single pile with the pile group with the pile spacing of 2D, 3D, and 4D. The pile which is placed at a 4D has a lesser deformation than that of the pile placed at a distance of 2D. It means the pile, the front row of pile, which is on the active wedge zone, whereas the rear pile is away from that of the active wedge zone. Therefore, the front pile acts as a shadow to the rear pile, whereas the rear pile supports the front pile through that of the pile cap. The rear and the front piles are complementing each other. Because of that, the deflection of the pile is
You have 4 more minutes. Can
this is the moment variation of the pile group. Then the front pile has a moment variation, particularly the top part, the moment is negative, whereas the rear pile, the moment is positive. The contraflexure point is very close to that of the depth of excavation in case of the front pile. This is the variation of the normalized displacement with inverse depth embedment ratio of the pile. When the length of the pile is more than the depth of excavation, the deflection, normalized deflection is reduced. Now, this is the effect of number of piles, both in displacement and the moment, as well as the ratio of maximum of positive, maximum of negative moment. Increase in number of piles, the moment in the pile group, the moment in each pile reduces when compared to the moment of the single pile. This is the response of the pile subjected to axial load. Then we have considered the axial load of different capacity, because the axial load on the corner pile, axial load on the central pile group, axial load on the edge pile group will be different. Therefore, different intensities of axial load has been considered. The deflection of the axial load of pile is more than that of the pile without axial load, because the shadow effect of the front pile is reduced, and then pile has a tendency to rotate or deflect when the axial load is acting on the pile. This is the moment variation of the both front pile and then the rear pile. Due to the axial load, the negative moment increases, as well as the positive moment also increases when compared to that of the pile without axial load. This is a comparison of non-dimensional displacement of the pile group with that of the ratio of the axial load. You see that the piles with the LBD ratio more than 20, this normalized displacement is not showing any change. And then the short pile undergoes a larger displacement compared to that of the longer pile. Next is the application of the axial load, the tie force on the pile group. The tie force is applied on the opposite to that of the direction of the excavation. Because of the shortage of time, you can see that the moment change due to the tie force, okay, the moment in the front pile is reduced by means of the tie force, whereas moment in the rear pile is increased with that of the tie force. The numeric analysis has been simulated using Flax's 3D model. Moore-Coulomb material has been used for modeling the soil mass. The major problem is selecting the modulus of the material. We have conducted light cone penetration test and then compared with the standard SPTN values. Finally, we adopted the value obtained from the plate load test, that is the E has been adopted. Now, this shows the comparison of experimental as well as the Flax's values, excavation depth versus the pile deflection. Similarly, the moment, it compares reasonably well.
Professor Ilamparathi, can you
another minute, sir, I will complete.
Okay.
This is the response of the pile due to the soil movement. This is the rigid pile fails by rotation. The longer pile deforms as a cantilever beam. The bottom part of the pile below the cut remains almost vertical because of the higher passive resistance. This is the preliminary strain zone. This is the secondary strain zone. When the pile is placed, the primary strain zone is being intercepted by the pile. Therefore, the deformation of the pile has been reduced. Now you see that this is the comparison of the deformation zone due to that of the short pile, intermediate pile, as well as the more flexible pile. This strain zone is confined because of the presence of the pile, as well as the secondary zone also having a lesser strain level. Finally, when the piles are placed beyond the distance of 0.6 times DE, the ground movement is not having influence on the deflection as well as the bending movement. What is the takeaway? Finally, we can say that in case of passive pile, the piles, if it is going to be within the distance of 0.6 DE, they will be subjected to displacement, and then bending moment also going to be more. When the pile location is beyond 0.6 DE, then the influence due to the ground movement is very limited. When the pile length is going to be more than twice that of the depth of excavation, then the soil movement is not having much influence. The tie force is totally changing the stress system. Thereby, the deflection of the pile is almost nil, or there is going to be a negative displacement. Thank you for listening. This is the work of one of my PhD student, Dr. Madhumati, and I acknowledge the support of Madhumati as well as Krishna Kumar in preparing this presentation. Thank you, Ananda.
Thank you, Professor Ilamparuthi. A very interesting lecture. Sorry, we had a limited time. The topic is very important, particularly because of a lot of metro construction in many of our major cities. I request Sri Aniruddhan to give a few remarks, and I think for want of time, we'll not have question and go to the next lecture. Thank you again, Professor Ilamparuthi.
Thank you, sir. Thank you for the opportunity given.
Yeah, thank you, Professor Gandhi and Professor Ilamparuthi for a wonderful presentation. I do not dare to sum up this excellent presentation, but however, I have to just say that it was very insightful, and especially when we have several deep excavations in urban areas where existing structures are on deep foundations, and many excavations are done very close to these foundations. So this study will help them to actually design the retention system without causing any distress to the existing pile foundations. Thank you very much. Thank you, Professor Ilamparuthi, for a very wonderful.
Thank you, Chair and Co-Chair, as well as the organizer.
Thank you.
Thank you. So can we check whether Professor Susan is has joined us?
She has joined.
She is available. Yeah.
Okay. Okay, good. Welcome, Professor Susan, to this plenary session 4. And it's a pleasure to have you with us. And I will have a pleasure to just introduce you to the audience before you can take about 25 minutes for your lecture. Professor Susan is a civil engineer from University of London in 1994, and she was awarded PhD in the University of Southampton in 1998. Then she joined department at Cambridge University, and then she moved to Australia at Centre for Offshore Foundation System at University of Western Australia. Susan rejoined the University of Southampton in 2017 as Professor of Offshore Geotechnical Engineering and was appointed as a Deputy Director of the Southampton Marine and Maritime Institute in 2018. Susan holds a Royal Academy of Engineering Chair in Emerging Technologies in Intelligent and Resilient Ocean Engineering. She has authored 2 textbooks, Offshore Geotechnical Engineering and International Offshore Foundations, and she is co-editor in many of the proceedings. Professor Susan is a fellow of the Institution of Engineers Australia, fellow of the Institute of Civil Engineers UK, and convener of the International Standardization Organizing Committee responsible for developing industry standards for marine soil investigation and offshore geotechnical design. Today's Professor Susani will be talking to us on topic, a new philosophy for offshore geotechnical design, theory and practice. Myself, having worked in the field of ocean engineering at IIT Madras for over 8 years, I know how challenging it is not only to investigate offshore, but also to have any foundation execution or design offshore. So we are all eagerly waiting for you, Professor Susan, to hear you. And please take the stage. Thank you very much.
Thank you very much, Professor. So I just share my screen there. Can you see that okay in presentation mode?
Yes. Go ahead.
Wonderful. Let me just put this over here. Okay, well, thank you very much. And thank you for the invitation to present at your conference. And so, yes, I'm going to share some thoughts on whole life design, theory and applications of this new approach to offshore geotechnics. But before getting to the technical paper, let me share a bit about where I'm based. So I'm from Southampton University, which is on the south coast of the UK, about 100 miles south of London. And it is a large port city with an established manufacturing industry for wind turbine blades. So we have good maritime pedigree, but perhaps most well known for being the port of departure of the ill-fated Titanic. At the university, our maritime engineering facilities are located on our Boldwood Innovation Campus, which we are co-located with the Lloyd's Register Global Technology Group. And in this building on the left that you can see there, that's the headquarters for the Southampton Marine and Maritime Institute, which is a pan-university institute that addresses global marine and maritime challenges across all disciplines and across all sectors in the space. So my day-to-day engineering home at the university is just across the path from those two buildings you can see in the top right at the National Infrastructure Laboratory. And there we have some fantastic new geotechnical laboratory facilities, including an element testing laboratory and a new geotechnical centrifuge. And a couple of years ago, I was very honoured to be awarded a Royal Academy of Engineering Chair in Emerging Technologies for Intelligent and Resilient Ocean Engineering. So back to whole life design, theory and applications of this new approach to offshore geotechnics. So there is a full paper that will accompany this keynote presentation, and it's going to be published in the special issue of the Indian Geotechnical Journal in the new year. And so today I'm just going to touch on some elements that are covered in that paper. So what do I mean here by whole life geotechnical design? Well, in a nutshell, the philosophical basis for whole life geotechnical design is that design outcomes can be improved by considering whole life actions and the resulting whole life responses. So the fundamental basis of whole life geotechnical design is the same as that for traditional geotechnical design, i.e. that the design action does not cause a design limit state to be exceeded. However, in a whole life design approach, this check is made repeatedly throughout the life of the structure or system, rather than just once for the worst case combination of maximum action and minimum resistance or stiffness, as is generally the case for traditional offshore geotechnical design. So this schematic illustrates the varying imposed actions and geotechnical response across the design life of an arbitrary structure that underpin the philosophy of whole life geotechnical design. So the imposed actions cover a temporal spectrum, and these may be short-term events. So they could be the undrained installation or an impact or snag load during the operational life or retrieval at the end of life. There can be longer episodes, which may be comprised of a series of events, for example, construction or operational processes or extreme weather events as illustrated here, or actions over the whole life of the structure. These could be periodic thermal events such as freeze-thaw or operational heating and cooling, or normal weather events offshore, or a displacement controlled activity like ratcheting. And these events and episodes can be superimposed on a background of the whole life actions and response to enable greater scrutiny of specific activities or environmental influences. So considering this hypothetical time history of actions, it's essential to understand, for example, what is the soil strength and stiffness at the start and end of episode B. So that is a storm in this case, and that will allow us to determine the true geotechnical stability of the structure during the episode and subsequently for events such as C or D. So from the figure at the bottom, it is clear that the design resistance for whole life geotechnical design, which is shown in green, always exceeds the current design action, which is shown in grey, while adopting a maximum action and minimum resistance across the design life, as is adopted for traditional design, which is shown in red here, leads to the design resistance to fall below the design action, which would violate the failure criterion. So in practice, this would result in a larger foundational anchor being required, which would increase challenges associated with installation and cost, both direct and embodied carbon cost. Now at the decommissioning stage, should the structure be removed from the seafloor, the whole life design approach enables a realistic prediction of resistance at the end of design life in order to inform on the required crane or vessel capacity, for example, while traditional design would considerably underpredict the actual uplift capacity. So if it were proposed to leave the structure in place beyond the original design life, whole life design can better inform on the stability of the structure for that afterlife. Now, the geotechnical concepts underpinning whole life geotechnical design are not new, and aspects of whole life design are established in onshore practice, although perhaps without being named as such. So staged embankment construction and tailings dams designs are based on whole life design principles, with consolidation as a driver to improve resistance for further stage of construction. In offshore geotechnical practice, there are examples of reliance on self-weight consolidation beneath the structure between installation and the winter storm season, but this is an exception rather than the norm. However, whole life geotechnical design is emerging as a more widely applied philosophy to encompass approaches that improve design outcomes by predicting evolving soil parameters due to imposed actions during the design life. And these insights can be applied at the initial design stage for optimal sizing of a foundational anchor, through life for assessing or predicting cumulative displacements or changes in resistance, and also challenging assumptions in the initial design against observed performances. And by extension, these insights can be used to predict actual remaining design life for relifing or repurposing or during decommissioning. Now, the soil responses that could cause changes in resistance and stiffness over time can be due to various factors, including consolidation, due to changes in applied load, whether they be monotonic or cyclic, sediment transport, so scour and erosion, leading to a change in the seafloor profile, or cyclic strain, ratcheting, for example, accumulation of deformation under cyclic actions. So just to recap, so whole life geotechnical design seeks to predict soil structure responses across the design life by considering the whole life of imposed actions coupled with geotechnical properties that evolve with each action. The geotechnical properties can evolve throughout the design life of a structure due to the actions that are imposed during installation, the operational life, or late and end of life management of an asset. Whole life geotechnical design checks limit states at different stages of the whole life against the current geotechnical properties, which are updated based on the processes that have occurred and the responses that have accumulated earlier in the design life. And consideration of whole life geotechnical response provides greater insight, enabling forecasting of the response of a supported structure through and beyond its design life. So why do we need whole life geotechnical design, and why now? There has been an established offshore sector for oil and gas for more than 60 years. Some 5,000 oil and gas platforms and structures have been installed in oceans globally, and generally without much issue, suggesting that offshore geotechnical design practices are okay. But the transition to renewables has seen an acceleration of installations in the oceans, more in the last decade than in the 50 years before that, and with a much lower return on investment than for hydrocarbon facilities, because more structures are needed for an equivalent energy yield. So designs must become more efficient or optimized and appropriate for the shift from bespoke individual platforms carrying a crew and hazardous materials in the hydrocarbons industry to developments of tens or hundreds of self-similar structures without a crew or hazardous substances for renewables. And people are increasingly looking to the oceans as a strong renewable energy resource and as a place with space for development. With a population forecast to increase to 9 billion by 2050, 11 billion by 2100, it's been suggested that without changes in our behaviours, we will need 4 or 5 planets to sustain our growing demand for resources. and oceans covering 70% of our planet are often seen as an empty space for this development, although arguably oceans are full and busy places supporting ecosystems that ultimately support us. So there is a diversity of industries moving to the oceans that have lower return on investment than oil and gas, not just fixed and floating wind, but tidal and wave energy, and also cables networks for communications and power. 99% of internet traffic travels along submarine cables. There is also floating solar, potential for greater aquaculture, and industrial applications, for example, floating ports or new concepts of energy islands, and even urban uses of offshore space for seasteading. Now, considering just the UK outlook from where I'm based, there are various projections for offshore wind provision by 2050. The UK 6th carbon budget sets out a range of scenarios indicating between 90 and 140 gigawatts of offshore wind by 2050. This corresponds to a build rate of up to 5 gigawatts a year, or approximately 1 offshore wind turbine built every day for the next 30 years. And there is a challenge of where to put the structures to deliver the necessary capacity. And at Southampton, we're carrying out a project looking at existing and forecast constraints in terms of offshore wind farm development, whether those constraints be metocean or ecosystem, geoscience or anthropogenic. And while the oceans are big, the most accessible bits can be quite congested or home to significant or endangered ecosystems or difficult metocean or geoscience conditions. And there is a similar outlook in many regions. Globally in 2021, there were more than 5,000 offshore wind structures and a touch under 3,000 oil and gas structures in our oceans and seas, and an exponential increase forecast for wind in the coming decades. So this study from Southampton collected a data set of historic, current and forecast offshore hydrocarbon and offshore wind infrastructure globally over the period 1960 to 2040, and we've presented it on an interactive GIS map against a backdrop of offshore renewable and hydrocarbon resources. And that map is freely available alongside the open access paper. And the data shows a shifting loci of offshore activity in the coming decades. And the paper explores some of the tensions of balancing the economic, environmental and social needs in current regulatory frameworks. And wherever all this infrastructure will be, it must be secured to the seabed efficiently and effectively. And this is achieved by a range of foundation and anchoring systems. And often in very variable geotechnical conditions. This is an example from the Burbo Bank extension site in Liverpool Bay in the UK. And we can see that just along a single line of CPTs on a 10-kilometre section shown in red in the top left figure, you can see the variation in soil properties by the CPT profiles below. So just to recap again, we've had a look at what whole life geotechnical design is and why we need it now. Now, the general philosophy of whole life design applies to all situations in which the strength, stiffness and other soil properties evolve over the life of a system. But the focus on this presentation is going to be on consolidation-driven changes in soil properties. So considering this figure again, in the context of evolving soil properties from whole life shearing actions and consolidation, fundamental soil mechanics principles describe the mechanisms through which undrained monotonic loading of a clay soil leads to increases in excess pore pressure and reduction in effective stress. And it is well established that undrained cyclic loading leads to softening due to the buildup of those excess pore water pressures. And consolidation, so dissipation of excess pore pressures and reduction in void ratio, leads to increases in undrained shear strength of a soil. And in sequence, these principles form the basis of whole life geotechnical design with consolidation as a driver. Now, softening in fine-grained soils from undrained cyclic loading has been observed in laboratory element tests and captured by pore pressure and strain contour diagram approaches for decades. Cyclic hardening is less well observed and captured though. And these two plots show cyclic softening and cyclic hardening observed in flow around penetrometer tests in normally consolidated kaolin clay in geotechnical centrifuge tests. So the flow around penetrometer is an alternative to the cone penetrometer test, and an example shown on the right here, where a perpendicular shaft replaces the cone at the bottom of the shaft, and sometimes a ball replaces the cone too, but the principle is the same. So the benefit of the flow around penetrometer is the larger surface area, which gives a higher resolution of measurements in soft soils, and also the large projected area of the bar or the ball relative to the shaft leads to equalization of pressures above and below, eliminating the need for overburden correction. And they also enable full remolding of the soil to take place through cyclic loading. So on the left, the penetrometer is cycled at a specific depth continuously without the opportunity for drainage. And that reduction in penetration resistance with increasing number of cycles is clear. In the lower plot, it's shown that the undrained shear strength, in this case, halves in the fully remolded state compared to the initial intact strength. So in the test shown on the right, the penetrometer is paused between cycles to enable dissipation of excess pore pressures, from which an increase in penetration resistance can be seen with increasing cycles. And in the lower figure, we can see that up to a 3-fold increase in strength can be observed compared to the intact value. And so this provides a very wide range of potential strengths to use in engineering design calculations, demonstrates the importance of using the appropriate resistance across the design life of a structure to ensure an effective but efficient design. So the paper elaborates on a number of other examples of observed changes in soil properties, not just strength, but stiffness and coefficient of consolidation too. But for the presentation, we need to move on now to have a look at how to move from observations and measurements of whole life soil response to a design method. And this requires the identification or development of building blocks to capture and accumulate the individual processes, and a practical method for identifying the necessary input parameters to the calculation tool or framework. And I'm going to talk about 2 different styles of macro model that have been developed and that can be used to apply whole life geotechnical design to a range of boundary value problems. And both of these methods use critical state soil mechanics principles as the building blocks. Since critical state soil mechanics neatly relates changes in stress, excess pore pressure, and changes in volume, and hence strength, stiffness, and coefficient of consolidation. So critical state soil mechanics is traditionally visualized in EP and QP space, as shown here on the left, and whole life or episodic loading with intervening consolidation can be very neatly captured by the same framework. So we've illustrated that here on the right for the case of a constant vertical load, shear to failure in each episode of shearing, and full consolidation between each shear period. And then this can be linked to the hardening or the strength increase through the stress volume relationship shown at the bottom. Sorry. So the first of the macro models I'm going to talk about adopts a lumped or a layered approach. So this is a simplified analytical approach to model critical state soil mechanics principles to lumps or layers rather than individual elements to soil to provide a generalized solution, which is sort of quick and easy to apply for preliminary design without the need for lots of finite element analysis. And it can be incorporated into a wider system model involving the structure using springs sliders. So the figure illustrates different modeling concepts and a simple spring slider analogy for each system, where the spring or the stiffness and the strength of the slider can evolve with time and loading history. So a lumped element approach, which is shown in C here, applies essential critical state framework principles to a region of soil, which is modified by a scaling factor or a lumped factor to account for the non-uniform distribution of stress and void ratio change over the region governing changes in strength, stiffness, and coefficient of consolidation, and can be represented by a spring slider as for a single element. And the general lumped element or macro element model has been applied to a range of boundary value problems, including shallow foundations, pipelines, and penetrometers. Now, the layered element approach, shown in D here, applies the basic critical state framework to layers, and this enables variations in soil properties with depth or stress level to be considered discretely and then summed. So that approach is analogous to the odometer method of predicting settlements. And this approach can be illustrated as a series of spring slider in sequence. And the layered approach has recently been applied to frameworks for predicting changes in resistance and settlement of tolerably mobile subsea foundations. So considering a simple case of a shallow foundation under vertical loading, self-weight consolidation can lead to a doubling of the initial undrained shear strength close to the underside of a foundation, decreasing with distance from the foundation. So the question then is, how do you determine the operative shear strength that will govern the foundation performance under the subsequent load path? So results from a suite of finite element analyses investigating the effect of relative preload, degree of consolidation and over-consolidation ratio show consolidated undrained vertical capacity of strip and circular surface foundations can be predicted by a simple lumped element critical state model, where the increase in capacity can be described by a simple linear function of known parameters. R, the normally consolidated undrained strength ratio, SU over sigma dash V, VP, the applied preload, i.e. the self-weight, and NCV, the vertical bearing capacity factor for undrained, unconsolidated conditions. So F sigma and FSU are the stress and strength factors that account for that non-uniform distribution of stress and void ratio change over the region. So this approach has been extended to multidirectional loading of skirted suction buckets and mud mats, enabling multidirectional consolidated load capacity to be predicted based on that simple linear expression, which holds for different load paths just through that scaling factor F sigma FSU. And in this case, applying the same fundamental critical state soil mechanics macro model to lateral breakout of pipelines following post-installation consolidation. And you can see, comparing the inner pink envelope to any of the outer ones, the effect of installation and post-installation consolidation on breakout resistance. So this is an example of the layered element framework applied to a tolerably mobile foundation. So that is a foundation that is engineered to slide across the seabed in response to the thermal expansion and contraction of the attached pipelines. And here we can see how self-weight and period of consolidation across the design life affect the evolution of settlement of the foundation. And to the right, the changes in sliding resistance and undrained shear strength that accompany those changes in volume responsible for the settlement. So the figures on the right compare observations from centrifuge model tests with that simple critical state soil mechanics based macro model that can predict changes in soil strength, sliding resistance and settlement very well. So critical state soil mechanics can be directly applied to lumped or layered zones to create a macro model for a boundary value problem if the representative stress state can be reasonably estimated, such as for shallow foundations and pipelines or other near surface infrastructure. For embedded structures, the representative stress state is not so straightforward to design, and hence deriving the effective stress to define the changes in void ratio is not straightforward. And so in this situation, a critical state inspired approach can be adopted using proxies of damage or softening and hardening to represent excess pore pressure, generation, and the dissipation leading to the change in void ratio respectively. So a damage and hardening analog critical state inspired macro model has recently been developed for soil that is on the wet side of the critical state. So for these conditions, undrained cyclic loading from the initial state generates positive excess pore pressure, which is captured by a proxy parameter, the damage index, which ranges between 0, no damage, and 1, full remolding. And consolidation causes densification through dissipation of excess pore pressures and a reduction in void ratio, which is captured by a time-dependent reduction in the damage index and an increase in the so-called hardening index. And the rate of hardening depends on the degree of excess pore pressure dissipation, which is shown in the middle figure. And this critical state inspired macro model has been applied to a lateral pile response, showing the evolution of stiffness with cyclic lateral loading, initially softening and then recovering back to the initial value. So the same critical state inspired analog has been applied to an embedded plate anchor mooring a wave buoy. And on the left here, we can see the effect of 3 years of seasonal loads on changes in strength, also shown as damage in the second plot and hardening in the lower plot. And these can be shown together, as in the figure on the right, which captures the initial state of 0 damage and 0 hardening, followed by damage during the initial loading, which is subsequently mitigated by consolidation or hardening with time to a final state with a strength in excess of the initial value. So alongside a computational framework, a practical method of determining the necessary input parameters is also needed. So the examples I showed at the start of the presentation of softening and hardening using the Fluorine penetrometers, these give good results, but they are not very practical for routine use, as they either need to be deployed in situ offshore at great cost, or sufficient material needs to be retrieved and sampled to enable centrifuge model testing and possibly large deck side tests. So some recent work at Southampton has showed that using direct simple shear element tests can demonstrate evolution of strength, stiffness and coefficient of consolidation necessary to capture the parameters needed for the critical state whole life geotechnical design framework. And some ongoing work is investigating the effect of packets of pre-failure cyclic shear with intervening consolidation, and we'll present those results in a paper next year. So just to recap again, we have had a look at what whole life geotechnical design means, why it is needed now, some of the theory underpinning the fundamental building blocks of whole life geotechnical response, development of macro models to do preliminary design calculations, and applications to various boundary value problems. So what else is needed to enable whole life geotechnical design to be adopted routinely? Well, I touched on site characterization and practical protocols for deriving necessary input parameters for whole life geotechnical design. We also always need ways to define whole life actions and then to measure or monitor those actions continuously to improve definition. Calculation tools need to be accessible so engineers can use them. And an example is the freeware web apps that I host. Verification via field data will be essential to build confidence in adopting whole life geotechnical design. So operators need to come on board and collect and share performance data. And for widespread adoption, formalization of guidance is needed, so incorporation in international standards. So looking forward, the oceans are being industrialized at an unprecedented pace and scale, and technology and geotechnical engineers do have a vital role to play. Efficiency and optimization of geotechnical design is essential to enable the offshore renewables transition necessary to support decarbonisation of the global energy sector. And whole life geotechnical design has an important role to play. But we should focus our minds not just on what we can do to deliver the competing demands of growing population and reduce CO2 emissions, but also on ensuring that we do this as responsibly as we can, using technology to monitor the impact of our interventions on the oceans to inform better decision-making going forward. And there are a couple of articles on this open access site, The Conversation, that you could take a look at if you are interested. So just to close, I would like to make some acknowledgements to the team at the Centre of Excellence for Intelligent and Resilient Ocean Engineering, or IRO, and the wider group of maritime colleagues at the University of Southampton with whom I collaborate. I would also like to acknowledge the international collaborators, and particularly those whose work I have shown in the paper or presented today. And particular thanks to the Royal Academy of Engineering, who support my chair in emerging technologies and intelligent and resilient ocean engineering, and the wider academic consortia and industry supporters of the work of IRO. And finally, to thank you again for the opportunity to present and for your attention today. Thank you. I think you're still on mute, Professor.
Professor Gandhi, you are on mute. You're speaking something.
So thank you, Professor Susan, for the very interesting lecture. As you may be aware, we have a long coastline compared to the area of the country, and there is tremendous potential for the wind, offshore wind energy. Though it is yet to be explored, some of the companies like Suzlon have already identified 2 or 3 locations, but the challenges in building the offshore foundation, I'm sure we will overcome that, and your presentation will be of use in that. And we look forward to hear from you in future and have an interaction with you as and when possible. Thank you once again for a very interesting talk. I request Professor Sri Aniruddhan to have his remarks, please.
Yeah, I have one simple question, Susan. So, are you suggesting that we use the minimum ratio between the action and the minimum resistance in the beginning?
So no, so that isn't really possible. I mean, certainly there are opportunities to use the concepts that underpin whole life design to minimize, optimize the initial foundation size if you rely on, for example, consolidation after installation, prior to when you know the first of the significant storms or waves will come seasonally, for example. Over the life of the structure, if you observe how the performance of the structure is compared to your predictions, then you might be able to extend design life, for example, which will reduce the embodied carbon of your assets, obviously be more productive if you can extend the life beyond what your initial predictions were. And then there are benefits, you know, for actual decommissioning processes and late life management. So I think, you know, the notion is of applying whole life geotechnical design across the design life rather than just as a tool to use for initial design, and then you'll put it in the drawer until it's, you know, 25 years is up and you go and decommission it. Because of course we don't know when the 1 in 50 year storm is going to come.
Yeah, understand.
But across the whole development, you can use reliability analysis then to monitor the sort of increase in factor of safety of your whole development as the soil properties improve and the design storm has not yet arrived. So that might give you greater design life in the long run. I hope that answers the question.
Yeah, another thing I noticed is you have given more emphasis on the strength parameters in future, but not so much on the volume changes, which will affect the performance.
Absolutely. So I suppose the volume changes in the undrained and consolidated methods are directly related to the volume, and the strengths are interrelated through the void ratio, but also equally to other geotechnical properties like the stiffness and the coefficient of consolidation. So all are important, and particularly for fixed wind, these are governed so much more by stiffness now than stability, which was the case for offshore oil and gas structures. So I showed one example of settlements of a shallow foundation. And in that case, actually knowing what the settlement was is also important, but linked to that settlement is the change in strength, stiffness, and coefficient of consolidation. So I suppose in that particular case of the surface foundation, people might be interested to know what the settlement is. Whereas in other cases, say for a laterally loaded pile or something, you might be less interested in settlement, but more interested in the change of stiffness or the rate at which that change in stiffness is going to continue, so therefore stop, in order to be able to assess your fatigue limit state, for example, your fatigue life.
Thank you. A very wonderful presentation. Thank you for the presentation. Yeah. Any questions are there? I don't see any questions.
Okay, so I think on behalf of my co-chairs, Sri Aniruddhan, and for all of you, let me thank both the speakers, Professor Susan and Professor Elamparuthi. Please join me in giving a hand to the very good presentation by both. So before I hand over to the organizers, I would like to convey my sincere thanks and gratitude to the organizers
Yeah,
for providing opportunity.
Sir, we have couple of corporate presentations in these sessions.
Fine. Okay. Yeah. please
So
go.
I'll see.
Yeah,
We have Sri Infrastructure and Emil Muthukumaran.
yeah.
We have two, yes.
Emil and 000 Geotech.
000 Geotech. Sri Infrastructure.
I hope there will be a
There's
video.
first
Yeah.
First one is Sri Infrastructure.
Excuse me, sir. Excuse me, sir.
Yeah.
Sir, excuse me, sir.
Yeah, please.
Sir, from Sri Infrastructure, they have informed us that they won't be able to join the session today. So instead, meanwhile, we have played that video. Now we can move on to the next presentation, sir.
Is Emil is available?
Yes, sir. We are there, sir.
Yeah, please present.
Let me know if my screen is available.
Yeah, you can make it in show mode.
It's in slideshow already.
No, probably you have to reshare the slideshow.
Okay.
You have shared the edit mode.
Just a minute. Is my screen visible now?
Yeah, not in, make it show mode. Yes. Yeah.
That's fine.
Yeah,
Okay.
you can remove the review side. Next slide thing you can remove.
Yeah. Probably you can duplicate the screen.
No, right click, hide presenter view. Yes.
Yes. Yeah.
Is it fine now?
Yeah, it's fine. Yes.
Okay. Good afternoon, everyone. And I thank you all for giving Emil Limited an opportunity to make a presentation on this prestigious platform. So without taking much of the time, I'll proceed with the presentation. I think I have 8 minutes, right?
Yes.
So we, Emil Limited, are a 1932 established company. We started we started basically as an instrumentation manufacturing and trading company, providing services to various civil engineering, analytical, industrial, electronics, and healthcare industry. And quite some time back, maybe around 20 or 25 years ago, we started consultancy services also. So today's presentation's focus will be on the consultancy services of Emil Limited, though I'll give a brief introduction about our company. The mission of our company is to provide optimum quality and customer service by bringing new innovation and new ideas from the world globally, right? We have been awarded as best professionally managed company in year 2019. Today we have 900 plus employees. Most of them are graduate or master's degree, have master's or graduate degree in engineering in the respective fields. We have 14 in-house testing and calibration laboratories. All of them are covered under NABL umbrella. And we have catered to around 25,000 plus satisfied customers. In addition, we have overseas partnerships with 100 plus international companies of repute. And we have a presence almost in all major cities of the country. This is our global presence in India. So you can see that we have our offices almost in all major cities of India to cater for the need of local customers over there. And the manufacturing units are based in Delhi and Noida. These are our partners. We have partnered with all of them to provide exclusive services supply in India. So again, we are a ISO 9001 company. We have calibration tests labs, testing labs, as well as field entity, which includes carrying out cross-hole surveys and pile integrity testings, non-destructive testings of concrete. All these activities which we do at field are also covered under NABL umbrella. In fact, we are only a few companies in India who have NABL for field testing services. We also are registered under National Small Scale Industries Corporation, and we have our in-house R&D lab, which is well recognized by Department of Science and Technology, Government of India. There is a list of services which we provide. So today's focus will be on civil engineering consultancy services, and I am myself in that same department, which provides services for consultancy in civil engineering. This is called Advanced Technology and Engineering Services Department of AML Limited. The department was started by Dr. V.M. Sharma, and today we miss him, sir. He very recently passed away, and I request all of you to give a minute of tribute to him once we are finished with this. Dr. Sharma took the lead role in starting the consultancy division of AML Limited in 1995. Until then, we are just running without any stop. We do provide consultancy services in almost all areas which infrastructure requires. Like we do test investigations and testings for desktop studies, feasibility studies, DPRs, and detailed design. Then we ourselves have design and data analysis department for geotechnical engineering. Then we do instrumentation on monitoring of the structures, and we also do the non-destructive testing of built structures. This is the list of projects which we have already executed. I mean, this is only a few of them. There are many more to come. Field investigations, we do topographical survey, we do geological investigations, geotechnical investigations, we do field soil and rock mechanics testing, and we also do some geophysical investigations. These are the topographical survey. We also do bathymetry survey nowadays. We have recently started this service. Geological survey, we do geological mapping of the area, and we prepare the geological sheets to the scale which are required by the authorities. And geotechnical investigations. We do open PLT tests at site, SPT in soils and other tests. We also do direct shear test in fields, concrete to concrete as well as rock to rock interface. We do open DST with the different load combinations required by the client. We also do plate checking and tests which are required for various design of underground structures. Field altimeter tests. All the pictures which we are showing are our actual tests executed in India by our company. So I'll hurry because the time is little slow. We have our in-house NABL accredited lab to do all the tests. The geophysical surveys, we do ERT survey, we do seismic reflection survey, we do tomography, we do many things in that. Now coming to design and analysis, we get associated with the various infrastructure projects both during tender stage to help contractor preparing their tender bid, and we also do detailed design analysis. Some of the projects underground construction we have done using Plaxis 2D and FLAG 3D model are presented here. This is the twin tunnel which we have recently designed. I'm not here highlighting the projects. All the projects are executed in India, and these are the live analysis photographs extracted out of those projects. This is the seepage analysis and the drawdown analysis we did for some of the projects. We have also, for the first time, did vibration monitoring we were doing since long, but the first time for our Chennai Metro client, we did vibration analysis and prediction that because of tunneling activities, what is the expected vibration levels at different points, and then we also monitored it to verify it. We do building risk assessment and building condition surveys for underground infrastructure construction. So these are some of the works which we have done. We do building condition survey, as I already told you, building risk assessment. We also have done some projects for slope stability analysis using both limit state analysis as well as finite element techniques. We have modeled 3D as well as 2D analysis for underground powerhouse caverns and complete associated tunnels. We have also been associated for some failure mitigations. Like this was a slow failure mitigation, which we got Aerosol informed and provided a solution. There was a failure for some underground construction, which we analyzed all the monitoring data, and then we found out the reason of failure, and then we provided a solution that using micropiles protecting the further settlements of the associated buildings and also further deflections. Once we have designed the structure, we also get ourselves involved in instrumentation and monitoring. This is the instrumentation which we have done for underground D walls and metro structures. We have done instrumentation for landslides. We have done instrumentation for landslides using both geotechnical as well as survey techniques. And we have also done instrumentation and monitoring for some bridges nowadays. So we have developed our in-house software called Argus to present all the data in real time to the client. In this way, our software is capable of preparing self-generated reports. It's also capable of the figure on the left show an on-site visualization of the values which have been triggered. So it will automatically blow an alarm and give a red light indicating the site people to immediately evacuate in case certain values.
Amanda,
Just
can
give
you
me,
please, yeah.
Just give me 1 more minute. I'll sure wind up. So this is actually real use of instrumentation once the people get on-site visualization and alarms. Otherwise, just recording and analyzing afterwards probably is not going to help. So we have developed our own in-house software called ARMS. So as I discussed, we do cross-hole and pile integrity testings, all for underground elevated metros, all covered under NABL umbrella. So maybe I like to close here because of time, but in short, I'd like to say that we in NABL Limited are not only an instrument selling company, but we are a geotechnical consultancy company who provide consultancy services to external as well as internal clients. Thank you, sir. Thanks for your time, sir.
Thank you, Hemant. Yeah. I now request Mr. Raman of Triplo Geotech to make his presentations. Mr. Raman.
Hello.
Yeah, you have 5 minutes. Yeah,
okay.
You can take 5 minutes to finish.
Okay, I will open my PPT. Yeah. It's a demonstration. Okay. Is it working? Everyone can see our presentation?
Yeah, yes, you can start.
Okay, I will start. My name is Roman Donskoy. I am business development manager, international business development manager in this company, and I would like to present our company. So I will start that we have 30 years of experience in development and production of specialized laboratory equipment for mechanical testing of geological material samples. We are creating unique technology for geotechnical engineers, rock mechanical engineers, and mining engineers. So also I would like to add that our clients is firstly specialized educational institutions for training geotechnical engineers, geological engineers, and mining engineers. Academic and research institutes, specialized educational institutions for training geotechnical engineers, geological engineers, and mining engineers. Here's the range of our equipment. We have ProLine, SPEZline, and Standard Line. I will explain shortly about ProLine and SPEZline because it could be interesting for everyone, I think. So ProLine is a project composed system which is completed according to an individual order depending on the user's needs. This line consists of a power device with a capacity from 2 to 500 kilonewton pressure, pressure volume controllers with the ability to create a pressure from 1 to 70 MPa, testing cells and devices, a modular control and measurement system, so software based on APC. Here are some examples of our products. This is ProLine systems. It ensures the execution of tests with a high level of automation and also provides convenience in preparing for tests due to additional devices and mechanisms. Measurement instruments have right resolution and accuracy in a wide range of temperature and pressures. The control system allows you to manage load in real time with a high frequency of data updates. This makes it possible to implement such load modes as static, kinematic, dynamic, with stress and strain control. The hardware and software security system minimizes the loss of data and samples in the event of emergency and also ensures safety during the operation of the complex. Another one, this is SPEZline. This is we call it apparatus, so it's like big systems. that mostly is done for some special issues. So when our users are faced with complex tasks that cannot be solved with typical solutions, we offer specialized systems, Spätzlein, that perform complex specialized tests with increased requirements. Spätzlein systems are applicable for solving complex geotechnical problems in the development of underground space in the construction and mining industries. Distinctive features of Spätzlein systems are highly reliability and functionality for the implementation of the test method, which often does not have a standard. A high level of automation with the possibility of manual control, which makes it possible to implement both complexes, modes of force action, and to control the test process in manual mode. These systems can implement static and dynamic testing of dispersed soils, rocks, frozen soils under various types of stress state and under various boundary conditions. And some options of our warrantless technical service that we are providing to Russia and other nearby Russian countries too. You can see on the screen. Thanks for your attention, please.
Yeah, thank you, Roman.
I finished.
Yeah,
yes.
Thank you very much for finishing it in time. Yeah, Professor Gandhi, anything?
So I think let me once again thank both the speakers, Professor Susan and Professor Lamparuthy, and the three corporate presenters from Sri Infratech, AIMIL, and O Geotech for an interesting presentation. I am sure the participants will be highly benefited by the information given by the corporate presenters and also by both the speakers. I would like to thank the organizers for giving opportunity to me and the co-chairs, Sri Anirudhan, to be present in this session and interact with all members. Thank you once again, and I wish all success to the conference.
Thank you.
Thank you, sir. Thank you, Chair and Co-Chair.